This information is brought to you by Charles Sturt University.
Welcome back. So everyone, I think, did the second assignment on probability and counting. Some did very well, which is great. So has everyone been able to work out what mark they got? Has everyone? You can also go back and look what you got right and wrong as well, and you can see the correct answers. So the way to do that is you go to My Grades, you can see mark. If you click on the mark, it then gives you the feedback as well. So it's good to learn from it. It's always a good idea to learn from it. That's the whole reason we come to university. But also you have an exam, and question 2 of the exam has similar questions to it, essentially. And so learning from mistakes will help you prepare for your exam. So what we've done so far, there's sort of 5 topics, or 5 chapters, so to speak, of this subject. So this third chapter is looking at graph theory. So the third little segment. The first segment was sets and propositions. Second one was counting, bases and probability. So this one's looking at graph theory. So it's a neat unit. So I'm going to look a bit about graphs for a while, etc. So when you think of graphs in mathematics, you normally think of an XY plot, maybe some sort of picture. That's not what we're referring to. Maybe better thinking is the word network. So we're looking at how to represent networks. And they're sort of related, and it's called graph theory. It's a very useful way of representing data and the relationships between lots of data. That's what it's about. It's a really common data structure you see in computer science, or computers more generally, and that's why it's in this subject essentially. And there are some key algorithms that go with it, which are useful to know. So before giving theory, let's just look at some examples. So this is a part of a study called a sociogram, but it's just a graph really. So it's basically a bunch of kids in year 2, and that's all the initials there are the kids' names, and they had to pick up 2 people in the class they would like to sit next to. And if you got an arrow from yourself to someone else, that means you like to sit next to them. And that's pretty much what the outside was. What this was a study of doing this network across lots of grades in a school, just to see how social interactions change over time in a high school. Well, it was year 2, so I presume primary school from that one up. So it's been coded after the fact. The people in blue have no one who wants to sit next to them, the dark blue, and the white ones are the really popular people. And it changed. So people who are really popular in grade 2 weren't necessarily the ones that you look for later on, etc. Which is part of the purpose of the study. But what you can see here in terms of a graph is you have a bunch of vertices or nodes, so the circle in this case. You can label them sometimes, you don't have to. And there are lines connecting these nodes together, not necessarily all of them. This is a particular example where there's arrows, there's a direction to these lines. So this is called a directed graph. But you don't have to have that sort of line. So this is just an example. And you can see they're useful in describing sort of social networks. This one is. Speaking of social networks, this is another example. This is from Facebook. So this is another graph. So every location which there has a Facebook user represented by a dot. The brighter the dot, the more people, essentially. So then they have lines connecting cities together. If there's friends that are involved, if there's a friendship between someone in Sydney and Auckland, for example, there'd be a line connecting those 2 cities together. And the brightness of that connection is how many common friends they have. That's pretty much the idea. So it's interesting to see where people don't use Facebook. The most noticeable thing, actually, in the graph. So things like Russia is pretty, and China are completely absent from the graph.
So Africa, that's pretty cool too.
Now, in Australia, there's big parts of Australia that no one can use Facebook because no one lives there. I presume is the reason. So you can try to find where we are if you want to. But this is an example of another graph. So there's a bunch of nodes. The node in this case are smaller dots, essentially. So they're really, really small dots all over the place. You can see the lines connecting them, so they're called the edges. This one here is an example of a weighted graph, as in the brightness, how it's been displayed in the picture, depends upon how many connections there are. So you can have a node or an edge being brighter or darker than other ones. And that's the idea of being a weighted graph. So sometimes you might want to talk about not just how many connections there are, but some are more important than others. And you can see some really bright ones across the Atlantic here, for example, in the picture. So they've got a higher weight. You can do other simpler things. So this is a more simpler graph. So the vertices in this case are just different subjects that you might be doing, for example. Every time there's a person or a group of people doing both subjects, there's a line between them. So this is a simple picture. So the vertices are the subjects, and the lines, or edges is the common way of describing it. The edges are if people are doing both those subjects. Now, why would you want to do a graph like this? This is how timetabling systems work, essentially. So a timetable system effectively has a bunch of things you want to put on a timetable, so subjects in a real simple format, and you have lots of people. Every person is one thing is a different edge that you're adding to this little net graph. And the idea is you would like to give every individual a timetable so they have no clashes. That really amounts to assigning each of these different nodes, these different subjects, a unique time and timetable. That effectively means colouring it. So it just really means colouring the graph is effectively what a timetable problem is. So trying to find a colour for this so that no edge joins the hazards team. If any edge has the same colour for both ends, it means you've got a clash in the timetable. So you're trying to colour it so that people don't have clashes. There are no two adjacent colours. So the idea of colouring graphs, which seems something you might want to do in kindergarten or something like that, is a useful computer science technique to solve quite interesting and difficult problems like timetabling. And so graphs are a useful way of showing an abstract idea of what the problem is about. So it's a good way of showing relationships between different things. So there's some examples. So let's just try to talk about some things we can do about graphs, essentially. So that one there is not weighted and not directed. So just a simpler graph sort of thing. So definition. So a graph basically is a bunch of vertices. So written as G is equal to V comma E. It's a very abstract way of writing it down. So the V are the vertices. So it's a set of vertices. I'll sometimes call them nodes, or interchangeably really. And so they're the points. So in the previous ones, they were the points, or the little fine points, or the circles, effectively, just different ways to represent the same thing. Depends if they're right inside or not, really. Then you have a bunch of lines or arcs which connect these dots together. They're called the edges of the system. So you can write them as straight lines or as curved lines, whatever's more convenient. It doesn't really matter in some regard how you write them down. Depends on the context. So the Facebook one, we're using the greater circles along the globe. So vertices and edges. Depending on how you define things, you can have different sorts of edges, but I'll explain what some of those are. So that's basically the idea. You know what a vertex is and know what an edge is. That's the first two things you need to know. So what I'm going to do at the moment is I'm going to throw lots of definitions out there to distinguish in different types of graphs. And these differences are helpful in terms of knowing different things you can do with them, essentially. So you can have graphs with an infinite number of vertices. That's a little bit hard to deal with, so we're just going to focus on finite ones, make it a bit easier ourselves. That means a finite number of vertices and a finite number of edges too. So these are different types. So the first is the difference between a simple graph and a multiple graph. So you can see pictures down the bottom. So a simple graph means that every edge joins two different vertices together, and any two vertices have at most one edge between them. So explaining, so this one on the right, if it's not simple, it's called multiple. So what makes this one on the right a multiple graph? Well, two things. First, it's got a little loop down the bottom. So it's got a loop going from this node back to itself. So that's not allowed in a simple graph. That's one thing. So every edge has to just connect two different vertices, but it connects the same vertice to itself, essentially. So a little loop. So you can allow loops in multiple graphs. Sometimes you don't want those. So a simple graph excludes them. It's also multiple from the top. So these two vertices at the top have two edges connecting the two together. So it's really got two different edges. Again, that's not allowed in a simple graph. Sometimes we like that, sometimes we don't. So they both have uses, but it's good to understand there is a difference there, and some of you really don't want to enforce that you want just strictly one edge between two different vertices. You understand the difference? So I mean, I could ask questions like, give a graph, is it simple, is it multiple, etc. Other ones is if it's connected or not. So a graph is connected if there is any two different nodes, you can form take a bunch of edges and you get from one vertice to the other, essentially connected beams. So on the one on the left here, given any pair of nodes, I can find a bunch of edges, join them up, and get from one to the other. The one on the right I can't. Why not?
Because there's no line connecting the top left.
Yeah. So the top left guy, there's no edge connecting him to the rest of the network. So he's sort of by himself. That one, he's disconnected from the rest of it. And so you can do some things with a connected graph, but not others. So things like a minimum spanning tree, which is a useful algorithm, can only be done on a connected graph, for example. So knowing something's connected or not is useful in the grand scheme of things. And if the things are disconnected or unconnected like that, you can just sometimes you can apply algorithms just on one part and just them separately, sort of divide and conquer sort of idea as well. Next one's called the idea of complete. So a complete graph is one that's simple. So what does that mean? So that means there's only, as before, so no loops, and every pair of vertices have at most one edge. Well, a complete graph means every pair of vertices have exactly one edge. So everything's connected. Exactly one, essentially. So a complete graph is everything's connected exactly once. Incomplete means it's not, essentially. So the one on the left-hand side there is called the K4 graph, which is the complete. I don't know why K I use. So K for complete.
K for constant.
So it's called the complete graph with 4 vertices. What will the complete graph with 5 vertices look like?
Pentagram.
A pentagram. Yes. Yeah.
So K5 would be the complete graph with 5 vertices. Not a unique way of drawing it. You draw your 5 vertices in some pattern or other.
Pentagram.
You're right, that's what it looks like. So this vertice would be connected by an edge to all the other 4 vertices. That's to be complete. And we have to do the same thing for every vertice. So this one would have to be connected to all other 4. This one would have to be connected to all other 4. And likewise.
There's a circle around it. You put a circle around it.
That'll be a multiple graph then, and so complete graphs can't be multiple. I do get your joke. So that's the complete graph with 5 vertices. Now you can write it different. You can draw it looking differently. So you don't have to make it look like a pentagram. You really don't have to. You can draw it quite differently to that. We'll talk about 2 graphs being equivalent in a second. So that's complete versus incomplete. We can also talk about directed and undirected graphs. So a directed graph basically has arrows, so directions on the edges, essentially. So undirected has no direction. directed has directions. So I don't know if you can see very well from there, but it's got little arrowheads on all of them. Can you see it? Good enough. And they're both useful. So if you want to talk about the flow of various things, so you've got a bit of an irrigation network, you want to talk about the flow from one direction to another, you need to have directions. If you just care about friendships, the mutual friendships, they'll be undirected. But if you want to, like in the first example of kids picking who they want to sit next to in class, that's a direction, because you've got one person picking the other, but not vice versa.
Oh.
So that's a directional.
That's bad. There's like one kid that picks someone else and no one else picks him.
They get up and move away.
Yeah.
And that happened in that grade 2 class, unfortunately. If you're looking at the graph properly. So there was one kid that lots of other people picked, but there was a few kids that no one picked.
Oh, they
But-
on their own table.
So someone wrote a book, and they just showed how things change, the dynamics change over time. So both are useful, and they both have their own uses more and more. We'll focus on undirected for the moment. We'll do directed a bit later. A directed graph is often called a digraph for short. Digraph. And so digraphs are used in giving order to things. What I said is a data structure. So, I forgot what I was talking about. So, when I was looking at something about Android, so they have digraphs as an underlying data structure and how they show their computer flow or something like that. Sure, I should have remembered it better. But yeah, these are useful data structures that we'll see in when doing anything with computing, but also more generally. The other example, which is the idea of a weighted versus unweighted graph. So that Facebook example, when some edges were brighter than others. So what it really corresponds to is that when you've got edges, when you put a numerical value on the edge, that's really what a weighted graph means. So unweighted, all the edges are essentially equal. A weighted graph, they're not equal. That some are more important than others, and you value that by putting a number next to it. You can make them integers, or you can make them negative if you really wish, or you can make them fractions or decimals, etc. It's easier to deal with integer weights, so that's what we're going to focus on. But the system allows for anything at all. And again, they're useful from time to time. So sometimes you just care if there's a connection or not, but sometimes you want to choose between various connections. So if you've got so the classic example is the travelling salesman. A salesman wants to visit lots of different cities, and they want their path around the whole place to be as quick as possible. So they want to find and so therefore they need to know the distances they have to travel, and so that's the weight. And so minimising the distance travelled is key, and so therefore weights are really important. So it does depend on the problem type what you need to focus on. So as I said, we'll worry about weighted graphs later, we'll worry about digraphs later. We're just sort of flagging them. We'll just focus on the undirected, unweighted ones for the moment, which is the simpler ones, I guess. Okay, so just talking about some basic terminology with graphs, undirected graphs. So two vertices are adjacent if there's an edge connecting them. Just a simple definition, really. So just some terms. I want to talk about the degree. So the degree of a vertex is the number of edges that connect to that vertex. So you've got a little loop that counts it twice, which I'll just write an example, and we normally write it as the degree of this V. Let's do a little example just to help illustrate what it means. So this graph, make it bigger. So this has got four vertices, which I've labelled A, B, C, D, just to make it easier to talk about it. And it's got how many edges? The number of vertices is 4. How many edges does it have?
4.
So that's 1, 2, 3, 4, 5. So 5 edges. So we want to know a few things. What's the degree of A? So the degree of A is pretty much the number of lines coming out from A. Number of edges. It's 2. The degree of B,
3.
it's got 1, 2, the obvious ones, but also got 3 and 4. So it's only got 4 lines coming out of it. So I'll use different colour for it. 1, 2, 3, 4 different lines coming out of it. Now the fact that 2 of them join up together.
Is it because it's undirected? Would you be able to count those as 2 separate things? Because if it was directed, it would have like
Yeah, so if it's directed, then you would count the number of edges going out of it. In one, it's got an out degree, and separately we count the in degree number of vertices, number of edges coming into it. So in this case, the tricky part, which is what I put it in here, is that loop's really counted twice because it's going in on both the going in and the going out. It's being counted. That's the hardest bit about out degree, really. That's 4, and so that's the surprising one, probably. Degree of C, 3, and degree of D is 1. What does degree of 0 mean?
it's unconnected.
Yeah, it means it's not connected to the rest of the graph, but nothing's adjacent to it. What's that expression? So that's the, if you add up all the degrees and divide by 2, what do you get? So if you add up all the degrees, divide by 2, you get 5. What does that correspond to in this particular problem?
Amount of edges.
It corresponds to the number of edges. So that's true in general, as a matter of fact. That if you add the degrees up for all the different vertices and divide by 2, you'll get the number of edges. So that's the general rule. So if you add up the degrees of everything, you get 2 times the number of edges. Why is that true? I'm trying to explain why that might be true.
Because math. Because like if
A little bit more precision.
you have 2 edges. Wait. No, if you have 2.
There's 2 ends
Yeah, there's 2 ends.
on each line.
Yeah, as Paul said, Paul, you could probably explain it better.
There's 2 ends to each edge, so there has to.
There's one coming out of this end, one coming out of this end.
So basically, you just both the left and right hand side are counting edges.
Yeah.
So when you're counting the degree, you're just counting the number of edges leaving a particular vertex. And so if you're just counting up all the degrees, you're just counting the number of edges either coming in or going out. And as you said, an edge has 2 ends to it, so you're counting it twice, both the coming out and the going in, so to speak. And that's why you're counting everything twice, and that's why you get the twice number of edges. That's a simple reason, which is what you guys are trying to say. So, should have not given the answer. 30.
Oh.
There you go, memorised well enough.
I didn't miss
That's
that.
so loud.
So, if you had a graph with 10 vertices, and every single vertex has degree 6, how many edges does it have? Now, at first glance, you go, well, 30, that's correct. So, at first glance, it's good to realise that information, that's, how do you draw that? And the answer is it doesn't really matter. You can work out the number of edges anyhow. And so often you can answer questions about graphs even without being able to draw it, even if it has more than one way of perhaps figuring that sort of system. So how do you work it out? And the answer is 30.
6 times 10, and then divided by 2.
Okay. So pretty much every vertice would have a degree of 6, which is 6 plus 6, etc. up to 10 to get all 10 numbers. So 6 times 10 or 60 with a total sum of the degrees, and divide by 2 will be the number of edges. So the sum of the degrees would be 6 times 10, divided by 2 is the number of edges. So an undirected graph has an even number of vertices of odd degree. Do you know what I mean by that?
Yes.
So a vertex either has an odd degree or an even degree. It's got to be one or the other. So an undirected graph, some will be odd, some will be even. It has to have an even number of these vertices which have an odd degree. Why? So this one here, for example,
Is square and they're all connected.
had two vertices with odd degree, so there's two of them. That's an even number of them, essentially. So why is it true in general?
What's the minimum amount of vertices an undirected graph can have?
None, if you want to go for that.
Doesn't work.
If you want to be
Is it
trivial,
Is it really a graph though if it has no vertices?
it's called a trivial graph.
Like how can you tell it's a graph?
Because it's called a graph.
But there's nothing there.
But it's still labelled a graph.
If there's a math question and there's actually no math question there, is it really a math question?
Well, if it's labelled as a
It
graph, that's
corresponds
probably
to-
sure.
It's technically a graph. It's the empty graph. It doesn't look very interesting, I'm sure.
Is that going to be
Nothing.
phi too?
Hmm?
Is that going to be phi too?
Well, the collection of vertices is set, so that the vertices would be phi, and the edges are set.
So I guess
on
like
the
a
graph,
question
but
on
also
the sheet.
phi.
When the test is like, what is this graph? And there's just nothing there, and you're like, oh, okay.
I hope the image is copied into the exam. Otherwise, it becomes a bit easier. So that's the trivial graph, which is not terribly interesting, if you've worked out. But you can have, one edge would be, so one vertex is all possible. Again, not very interesting, perhaps. They get more interesting as the number of vertices increases. They get the complexity grows quite quickly.
So this rule only applies to like 4 and up vertices.
No. So if you had, say you had a graph with only one vertex.
Yeah.
If you allow it to multiple graphs, you can have loops, lots of loops. So for every loop, you'd have two ends, for example. So if you had 5 edges or something like that, then you'd have 10. The degree of this one lonely vertex would be 2 times that would be 10, which is an even number. So it's impossible to get an odd degree for a graph with only one vertex, for example, which is consistent with what I'm planning. So it's still consistent. It's just it's just 0 odd degrees. That's just an even number, which is still an even number. So 0 is an even number. I guess that's the thing that people may not always accept. Just like an empty graph is still a graph. That's might seem a silly thing to say, but the existence of nothing is a useful mathematical concept.
Just like a graph.
The existence of nothing is something.
And so, and
To be able to define nothing, you have to have a definition there for something.
where that comes useful is if you look at Roman numerals versus this number system that we have.
Is there a 0 in Roman numerals?
No, that's the
How do they do stuff?
nothing.
So how many sources do we have?
It's up there on the wall. There's nothing up there. I know.
Yeah, they had words for nothing, I'm sure, but they didn't. When they write down mass, they didn't have a symbol for
there's
0,
there's like 1 minus 1.
and that makes it much harder to do math.
At that point, they
But
didn't
anyway,
know what to do.
1 minus 1.
Yeah, 1 minus 1, they're like,
so back to answer the question: why does an undirected graph have an even number of vertices of odd degree?
we only have I.
No.
Okay. So we know that 2 times the number of edges, so an even number, is equal to the sum
Tricky.
of all the degrees.
I'm gonna drop this. I'm literally.
That's what we said before.
Shots of bleach.
So we could split that up into 2 bits. So we got summing up all different vertices. Let's make the sum over in 2 different groups. So the first group here is the degree of V is odd. The degree of V is even. It's sort of the sum we want. So in terms of what we had a second ago, so So the numbers we had were 2, 4, 3 and 1. So in our little example we had 10 was equal to the odd degree, so 1 plus 3 and 2 and 4. So that's what we're really doing. We just got the numbers 1, 3, 2 and 4. And we're just sort of reordering the sums, put all the ones together and all the even ones together. Essentially that's what we're really doing. So, therefore we've, just by rearranging this essentially, rubbing it properly, we can make this bit the subject. So the sum of, or the degree of the odd ones would be 2e, which is an even number, minus a bunch of even numbers. So my claim is that right-hand side is an even number. Does that make sense? Because you've got 2e, it must be even, minus a bunch of numbers which are all even. That's definitely is even. And therefore that tells you that this thing over here must be even too. So the sum of a bunch of odd numbers must be even. Now if you had one odd number, it's odd. If you have 3 odd numbers, it's also odd. So if you've got an odd number of odd numbers, it remains odd. If you have an even number of odd numbers, it becomes even again. You'll believe me?
Yeah, I'm going to take it as face value. If we had 1, 3, and 5.
So you get pick 2 odd numbers,
You get 9.
3 and 5. Add them together, you get 8. That's even.
What number of odd numbers equals an odd number?
Chuck another one in. Put another 3 in there. That gives 11, which is odd. Put another odd number in. Makes it 12. That becomes even. So you just alternate between odd being odd and even. So therefore, if we know that this sum of odd numbers is even, the only way of achieving that is if there was an even number of them. If there was an odd number, it just wouldn't work. It has to be an even number of them. So implies the number of, just easy to say the line. So the number of vertices with odd degree must be even, essentially. So graphs have been around a while. So just one little idea is called traversability. So there's 2 different ways of going around. Well, there's a few different ways of going around graphs. So this is just an interesting way. So a long time ago, so the city of Königsberg, I have no idea how to pronounce it. They wanted to have a little march around their town. So this town is located on 2 islands in the middle of a river. So there's a little picture of it. So B and C are the 2 islands in the middle of a river. A and D are the 2 different banks of this river. So the town pretty much has 7 bridges, if you can see there. 7 different bridges in their town. And they wanted to celebrate their town by having a march around the town so that they crossed every bridge exactly once. And this is a real problem. They really did want to do this. But they couldn't work out how to do it. And so they asked the most famous mathematician at the time, Euler, how to do it. That's pretty much what they did. And he said, you can't do it. Eventually.
How do we do it?
No.
You can't.
Okay.
So unfortunately, but in the process, it wasn't very good for these town people who couldn't really give them an answer. But it helped Euler develop this idea of how to
jump out and swim. Jump down and swim.
Well, if you're allowed to cross a bridge more than once, or allowed to just miss the bridge, then you can solve the problem. But so if you built another bridge, you might solve it. We destroyed one of the bridges in town. But that's probably not quite what the town people had in mind, I suspect. So you can represent the whole thing by a graph. So each of the different places you can visit, being the 2 islands and the north and south bank, are just the different vertices, and the bridges would be different edges. So you can see a one way of drawing that picture would be that sort of graph at the top. So this is how I was thinking about it. If you were to go around the town, so you crossed every bridge exactly once, then if you're in the middle of the path, so you're sort of in the middle of this big march somewhere, then you've had to have just crossed a bridge, and you have another one to cross. So they have to sort of match up, so they have to pair up in that regard. So if it's a vertex in the middle of your path, there really has to be an even number of edges coming out of that. So for every one you go in, you have to have a matching one that goes out. And so he argued that for every position in the middle of our path has to have an even degree. Whereas if you want to start and stop, if you want to start the path rather than just a big loop, then when you start, you have a starting point, so you have one that goes out, and then if you ever come back through again, you have to have one that's out. So a starting point would have to have an odd degree. And in a similar way, the finishing would have to have an odd degree. And that's how traversability would work. So what's the degrees in this case? So what's the degree at A in this picture?
3.
So 3, which is odd. What's the degree of B?
5.
5. Degree at C?
Another 3.
Another 3. So we've got 3 odd numbers already, and the last one?
3.
3. So for it to be traversable, you're allowed to have your starting and end point to be odd degrees, but everything else has to be even to be able to make your way around the town. To use every bridge exactly once. So the fact that all 4 of them are odd means you can't do it. So they built another bridge. So they built another bridge between A and C, for example.
This cold bridge.
That would make the degrees for A and C even now, and you could do it. Or if you destroy the bridge between A and C, would have the same similar effect. I don't think they really want to do either of those. But, so the general sort of idea is a graph is traversable, and I'll define it properly, is if there are either 0 or 2 vertices with odd degree. It has to have either 0 or 2, that's it. If it has no edges, if all the edges have even degree, that means you can do a whole loop, just go all the way around. That's called an Euler circuit. If you have exactly 2 edges with odd degree, then you can do a path from one to the other. Now, what I mean by traversable, it means you can visit every edge exactly once. That's what it means by traversable. So an Euler path or an Euler circuit are examples of visiting every edge exactly once, which matches up to the going across the bridge exactly once. So, let's have this. So let's change the graph to make it traversable. So the original graph was not traversable. This one is traversable. And the reason is because the degree of A and C are both even now, and the degree of B and D are odd. So now we know it's traversable, which means there is a path we can do by going around our little network here, visiting every edge exactly once. How do you work out what that is? And normally you can just do it ad hoc, really. So where do you have to start from? No.
Anywhere.
You can't start anywhere. So you can't start at C and you can't start at A. Why not? So you have to start at a vertex of odd degree. So if you've got any odd degree,
B or D.
So you have to start at B or D. So if you've got things with odd degree, you have to start at one of those two. So that's the starting point. So let's pick on B. That's where we're going to start from. Where we're going to finish up in the long run? The other one. So we'll have to finish at D. So D would be our end point. Otherwise, just have a go, really. You go, well, I've got to pick one edge. Let's pick one of them.
Get all the way down.
I don't like this. Let's go back.
So you can go all the way around. For example, just go all the outside loops. Then you can start going these ones here, and eventually you get to D in the long run. there's lots of answers if you think about it. There's not a unique way of getting around. But the way to work out a traversability, so what I did was B to A to C to D to B to A to C, B, D. That was my particular path I just picked down essentially. You could pick others. For example, you could have gone the whole thing backwards. Would also be trivially another one you could pick up. But there's lots of other variations from that. That you perhaps could do. So you could do B to A, back to B again, and go from there. So, once you've got the conditions for the traversability right, then working at in a way to go across the whole thing around, normally just a bunch of just trial and error for smaller graphs. For bigger graphs, it gets a bit harder perhaps, but in any assessment I'll give you, it'll be simple enough just to work them out correctly, if you need it.
Yeah.
So let's just do another version. Let's do.
Is that the Southern Cross? No. It's missing. I think a couple of points. It is now, however, satanic ritual. Shannon Knowles tattoo.
Okay, so this is the graph I just draw. Let's just add one more
It doesn't actually join up properly.
edge in here. So I just draw another edge from B to D. Let's look at the degrees. So just write the degrees in blue. What's the degree of A now? 4. Degree of C?
4.
Degree of D?
4.
And degree of B? 6. So they're all even now. So once the degree of all of them are even, it means that you don't have to have just a path. So you don't have to have a starting and end point. You can actually have a circuit and have one really big long loop which joins up. And because that loop will join every single edge together, you can start wherever you like, really, for one of these sort of things. So you could start an A, and you really just want to go around, as you're going around, you want to visit every edge exactly once. And again, you can sort of do it ad hoc. So I'll just put numbers, so just go around the outside. I'm just picking things at random, really. Just go around the outside. 5, and say 6, 7, 8, and then back to 9. And you can see the last edge I did went back to where I started from. But I could have picked anywhere else to start. So the lessons from this is you can work if something is traversable by looking at the degrees of all the vertices. If all the vertices have even degree, it means there'd be a nice big loop, big circuit you could do through it, or an Euler circuit. If there are 2 edges with an odd degree and everything else is even, then you could do a path, starting one of the odd ones and finishing the other odd one. That would visit every single edge. Any other arrangement of number of odd vertices would not be possible, would not allow you to have a transverse. Just like the original Kronecker-Berg, what's his name again? Königsberg, there you go. Königsberg town couldn't get their little march happening, essentially. So just some words that we've done here that sort of connect with this. So a path in a graph is basically being able to draw from one vertex to another. It would just been doing one edge after the other, like you'd expect. So that you can 2 edges can be used so long as they have a vertex in common. But pretty much, so long as you can just draw it on your graph, essentially. That's what a path is. We normally allow paths to be able to reuse edges if you wanted to. So sometimes we allow that. That's often fine. But if we want to have, so in a special case of being traversable, we would like to have a path which uses every edge exactly once. So I didn't have that exactly once there, really. So traversable is if it uses every edge exactly once. The length of a path is just the number of edges it uses. So I'll come back to some of these in a second. If it starts and finishes at the same point, it's called a cycle. Otherwise it's not a cycle. We've already talked about connected. So connected means any 2 different vertices have a path that join them together. That's what connected means. And again, it matches what we said before, so you can actually get from one to the other. You've got complete. So a graph is acyclic if there are no cycles. If there's no path which would have a cycle in it. So acyclic. So if something is both acyclic and connected, it's called a tree. And they're used for data structures in computer science. If it's something that, if a graph is acyclic but not connected, it's called a forest.
That's cool.
Why? Because it means...
Who thought of that? Who thought of that? I want to know who thought of that.
I don't know, actually.
He was like, oh, a tree. Forest.
Maybe he was smoking something green too. Wouldn't be surprised, so many freaking well-known people.
So that's an example of a tree. So it's a graph which has no cycles in it, it's all connected.
Fully drawn tree.
So it's an example of a binary tree even. So this is an example of a graph. So this is a disconnected one. So as in there's two parts to it. But each of these separate parts is an individual tree. So if it's disconnected but acyclic, really it's just a bunch, each separate component is a tree. So you've just got a bunch of trees.
So lots of trees.
And that's why it's called a forest.
Makes sense.
He was definitely high.
And so trees are a really common data structure, or having collections of trees, or a forest, is again a common way of representing data in computer science. And so lots of sort of techniques rely on that sort of stuff. So we'll look a bit more at trees later on, and they still are very useful. They're a special type of a graph, really. Okay. So two graphs are equivalent. Well, if two graphs are equivalent, we call them isomorphic, which is a very fancy word. Roughly, what that means is if you can morph or change one graph into another, then we'll call them isomorphic. I'll give a formulation in a second, but see if you can work out. So I've got four graphs there. Which two of... So give me a pair from those two which are the same graph, essentially.
B and C. Wait. No, A and B. Wait. No, A and B. I'm gonna lock in A and B. Wait.
I'd say A and D.
Yeah, let's go with A and D for the moment. Why are they the same?
And then C and B.
Because they don't have the same. They don't loop back and
They like linearly connect.
there's no, because it only goes in one way. Like you can't. The last stop doesn't connect back to the first stop in the.
So if you imagine them as being a bunch of strings,
Yeah.
right? You could bend A to D. Like you could, A is just a nice straight string. You could just curl it up to make it into D. So A and D are isomorphic.
Like you can't start with one.
B and D are also isomorphic. As in a bunch of strings, you could just, with C for example, you just fold down those middle two vertices to make it, and then spin around to make it look like B. So by just moving things around, you can go from B to C. B and A are not isometric. They're not the same graph. Why not? Well, one's got a loop, one doesn't. So the only way of going from A to B really requires ripping the graph up, or gluing it together. They're not allowed. So we're allowed to change it by rotating it, moving orientation, but you can't destroy or create any edges, essentially. What about these ones here?
A and B. That's what I think so for you.
Yeah.
What's back?
Maybe C and D.
So the top two are isomorphic,
Yeah, and C and D.
and the bottom two are isomorphic. And again, you can think, I can just move things around and it gets the same. So the formal definition is two graphs are isomorphic if you can have a one-to-one correspondence between the vertices of the two graphs. So I can map one vertex to another vertex. And when doing so, every edge in the first graph gets mapped one correspondent to every edge the other graph. Sort of makes sense, I guess. Out of those examples, which one's a tree? Any? So tree means connected and acyclic. So I know cycle, isn't it?
A and B.
So A and B are trees, that's right. And B looks like a tree as it's drawn, I guess. Upside down maybe. You spin your head upside down. So trees normally are drawn like that, as in they have a root and grows out. That's how you normally draw them. But A is also a tree, just because it doesn't look like one. It's still acyclic and it's connected. So it's a tree. Where C and D are not trees. Why?
Because the other things are connected.
Okay. Because there's a cycle in them.
Yeah.
So you can draw it. You can have a path which has the 2 points running up.
Good job, Corey.
Any trees in that one?
Trees.
Yeah.
A and D are trees.
So A and D are trees. Again, there's no cycles. Where B and C are not trees because there's definite cycles.
Is it itself a cycle?
Okay. That was the definition. So how we have a break for a few minutes, we'll come back to planar graphs.
It's a graph. So the next sort of graph I want to consider is what's called planar graphs. So a planar graph is one that you can draw on a piece of paper, it's on a plane, so that no edges intersect. So this is K4. What is K4? So K means the complete graph, and the 4 means 4 edges. So the complete graph of 4 edges. So that means every
Square.
edge
4 edges.
is joined everything else. So that's one way of writing it down.
It's like a crate.
Is that a planar graph? So at the moment, as I've drawn it down, 2 of my edges intersect each other. So I've got an intersection just right bang there, which means I haven't drawn it. I certainly haven't drawn it in a planar fashion just yet. Can I make that into a different? Can I change the graph so make it into an isomorphic form that can be drawn without any edges intersecting?
I assume so. Yeah.
How?
Take one of the corners and move it.
So just leave that. So you can start at that point. This last edge here, you have to join these 2 opposite corners. You can just go around the outside, for example. That's isomorphic. I mean, they're the same graph, just drawn differently.
It's like when you're trying to play connect the dots and you forget one of the dots and you're like, oh god, and you just kind of go all around all the other dots trying to fill it back in.
Yeah, I guess so.
You're like, oh god.
Stage childhood.
So this particular format here, I've drawn the graph so that none of the edges are intersecting. So if you can do that, it's called a planar graph.
So basically, it's a handbag.
If you want to, I didn't see it that way personally, but yes, I can see that now. So drawing like a handbag.
For David's face.
Some abstract art. Like,
So planar, as I said, so planar graphs are ones you can draw so that no edges are intersecting. So they correspond to a few different things. So I want to draw the whole graph differently.
don't touch me.
Okay.
Expensive modern art, go away.
So this also corresponds to, you can actually draw planar graphs. They can draw on a piece of paper, but they're also really spherical graphs. So you can draw them on a surface of a sphere. And so they correspond to a tetrahedron in this case, or a triangular pyramid is perhaps what you might know it as. So it's trying to draw a triangular pyramid. So a triangular pyramid, the base is a triangle. So that would be the base of my triangular pyramid, which has 3 edges to it, and you've got the top vertex at the top, so this would be the top of my triangular pyramid. So for any planar graph, you can draw it actually as a 3D shape that sort of, you can think of having a ball inside of it, sort of idea. So any planar graph, although you can draw on a piece of paper, you can also represent them as being some sort of 3D shape, and vice versa. So any 3D shape you can represent in terms of a graph. And if it can fully contain a sphere in it, then it's a planar graph. So, a little bit more to it than that, but there's more things to this, but that's a good start. So planar graph, draw it out any intersection. So here's another graph. This is called the K33. These simple ones have names to them. You've got 3 points at the top, 3 points at the bottom. So you've got 2 lines of 3 points. The K33 means every dot from the top must be connected to the bottom, one of the dots at the bottom. So this is like the utilities, classic utilities issue is you've got 3 utilities at the road, so at the bottom there, and you've got 3 houses, and you want to dig some trenches so that every house is connected to every utility, but you want to make sure the 2 trenches don't cross over each other. Can you do it?
Yes.
So is this a planar graph is my question really. So if I draw this one here, that connects all those 3 together. This one in the middle, so I can draw in here, I can go there for example, so that's a few, they're the easy ones. Then I have to start curling around to start making up the rest of them. So this guy needs to connect to those 2 over there.
Now you've just stuffed it up.
And
No, it's fine. You can.
if I don't, and the problem is I have stuffed up, I think you're right. I need one more edge.
You've already enclosed it in, so you can't get to it.
Yeah, so I really
Kind of like, you see the gap between the top line, you can go through the gap a little bit and kind of just get it in.
So if I draw it properly, the gap's disappeared.
Oh, no.
So,
Oh shit! Now what we do?
Yeah, this is really stumped me.
so you can see that I can't, well, my first attempt here, although I've tried to put lots of loops around, I haven't been able to draw it so that all the lines don't intersect. So there's a lot of intersection there. Is it possible to make it? Is this a planar graph? Is it possible to rearrange it somehow to perhaps get that? What's your hunch?
Probably.
Okay, yep. That's all I'm asking for. Good guess. So probably anyone say probably not or no? You can try it yourself and you get your own piece of paper out. You can work out what.
Go, Johnny, go.
What do you think? Can you try to? I mean, I've stuffed up here, but can you think of a different way of trying to draw those 3 dots at the top and 3 dots at the bottom, so that none of the edges intersect?
Yeah, there is a way. So the dots have to be like that, previously.
But 3 dots at the top, 3 dots at the bottom.
Did you do it, Jacob? Yeah.
I did it,
But you just get the middle one.
Are they intersecting?
no.
They're just about not.
You shouldn't be able to do it. It should be.
Well, I did it.
Isn't it like it'd only be possible like a 3D plane, wouldn't it?
Okay, it is technically possible, but not on a piece of paper.
Well, then you did something wrong, or I did something wrong.
I'll give you a look at it later. So this is not planar.
Oh no, because the bottom one will intersect when it's trying to reach up the top one. Yeah.
Doesn't have to.
So
Yes.
this one you can't do on a piece of paper. You can't do it on a sphere. You can do it with a little bit of trickery. I'll give my best to try to draw it. The trickery is to get a donut.
Delicious.
So you can do it on the surface of a donut.
Okay, everyone get a donut.
Okay, we'll be back in about 10 minutes.
Pull out your
15
math
maybe.
donuts.
So here's our little dot. So let's just try it again.
Give me on the sprinkles.
Okay.
6 at least.
So what do we need to do? So, so this guy needs to be connected up to here and.
You're just going to go around the donut.
So one thing we need to do is go all the way around.
What a
That's
mate.
one. That's one way of getting that one.
Go under the donut.
And this one goes round. Yep. And you can see I've actually drawn it on the surface of the donut with no intersections at all.
Basically, we're drawing Halo.
You just, all you need to do to finish this question is draw a donut as well, include other things in the question, and
Say M&Ms, maybe some Smarties, and
So-
jelly babies.
if you can't draw it on a chocolate cake, you can't eat chocolate cake.
Put it in the icing.
So the fun of it, so there's lots of maths here you can explore, but I'll just touch on the surface of it all. And so we'll come back to that in a second. But back to our much more simpler handbag, as you call it before.
That's such a bad handbag. How could you even...
So
When you actually hold it by the handle,
when you can write a planar graph, what it does is it neatly divides the piece of paper
I still use
into a bunch of regions. Each of these regions we call a face. So I just call that's called a name. So I've got face 1 here. That's sort of one sort of shape at that point in time. There's another one over here, and 3. So 2 and 3 they're just different triangles. And there's also one on the outside.
It kind of does.
Which is the outside of the graph.
It's Pac-Man.
So any
Well, Pac-Man's very, very, very special these days. Like,
He's just really hungry.
so he's like a snake. He's dislocated his jaw to eat the box.
Yeah.
His jaw like.
Any planar graph, which would include any picture you want to draw for that matter, and any way you want to visualise it, would split up the plane into a bunch of regions. Each of these we call a face. And so you can say like 4. So you got the obvious one's the inside. There's also the outside. So any planar graph would have an outside face as well. And it's sometimes easier to visualise with 3D. So this is my tetrahedron, which is exactly the same to it. So the faces are 2 and 3 are the sides here, 4's the back, and 1's the bottom. So you can see for a tetrahedron, so a triangular pyramid, you've got the base and then 3 sides on top. So there's the 4 faces. So it really just, and the name face corresponds to the 3D geometry it sits in. But you can see it, but even if you're drawing a piece of paper, you can see it's got the 4 different regions. So let's just do a few things here. Let's count. How many vertices does this graph have?
4.
They're all the same. They're all isomorphic, so pick any of them.
4.
4. How many edges does it have?
Would be 8.
Okay, let's do it differently. It's a complete graph. So a complete graph basically really just means choosing just 2 vertices to make any edge. So the number of edges would be, I've got 4 vertices to choose from. I want to pick 2 of them to make an edge. I want to have all possible. So the possible number of edges I can have would be 4, choose 2. So, and that is 6, as some people said. So combinations, mentioning again, crop up here as well. How many faces?
4.
4. So an expression that Euler worked out, this is called the Euler characteristic.
You do a lot of stuff.
Yep.
I don't know how you get Euler out of Euler.
It's like German or something.
I don't know. I can't even.
Are you telling me I've been pronouncing like Euler wrong all these years?
Apparently, it's pronounced Euler. Yeah.
Damn.
So it's written. Euler characteristic written is a chi, which is like a curly X character sort of thing.
Like Dragon Ball.
So the Euler characteristic is the number of vertices minus the number of edges plus the number of faces. That's the expression here.
2.
You could do it, and as long as you know, vertices and edges are okay, but you can do it for any 3D object at all. So if you had a 3D object like a pyramid, or if you managed to get that donut before and put some lines on it, just break it, split it up into regions, you can split up into faces, the donut as well. Then these sort of things make sense. What's that equal to in this particular circumstance? 2. So, a planar graph has the Euler characteristic equals to 2, and vice versa. So if you can work out the Euler characteristic of any particular shape at all, if it's equal to 2, then it implies it's a planar graph, and vice versa. If it's a planar graph, the Euler characteristic must be 2. So the study guide, if you're curious, proves that result using induction, by just looking at different ways of combining things together. So other sorts of shapes don't have a different Euler characteristic. So going back to this one here, this little graph here. So this graph splits up our donut into a bunch of regions. And we can sort of count the number of regions in this case. Okay, we're drawing all the edges I need to. Let's finish the picture off, put one more in over here. That makes it more correct that way. So, looking at my thing, so I've got 2 different faces in here in the middle. They're the interior ones. Then we've got one over here. This is face 3. But if you follow the lines round, that's face 3 over there as well. And if you duck underneath, that's face 3 as well. And that's face 3 as well. So pretty much you've got 1, 2 and everything else, essentially. The number of vertices? 6. It's got 3 at the top, 3 at the bottom. Number of edges? So you've got, from this first point, you've got 3 coming out. This one you've got 3 coming out. This one you've got 3 coming out. So it's 3 times 3 equals 9. Our number of faces? 3. So if you did the number of vertices minus number of edges plus number of faces,
Yeah.
you get 0.
0. What does that mean?
So Euler characteristic of 2 means it's planar. Euler characteristic of anything else means not planar. I'll give you more precision than that. So for graphs for anything that we could visualise neatly, Euler characteristic is an even number. The highest it ever gets is 2. That's the maximum. And so it's either 2, 0, minus 2, minus 4, minus 6, etc. So you can have them as negative if you want to. What value it is determined by the number of holes in it. So if there is no holes, it's 2. If it's got 1 hole, like our donut over here, it'd be Euler characteristic of 0. 2 holes, it'd be minus 2. 3 holes, minus 4, etc. So so what Euler characteristic is useful for in terms of classifying surfaces and graphs, related to that, is surfaces are complex beasts, but basically you can classify them simply by a number, so Euler characteristic, and that really just corresponds to the number of holes. And so just like we talked about 2 graphs being isomorphic, if you can morph one to the other, you can do the same thing with surfaces. So one surface can be morphed to another, like closed surface these, so long as the Euler characteristic is the same. And so this gives you ways of trying to morph things together. So a coffee cup, in a much broader sense, is isomorphic to a donut, for example. Because the handle on the coffee cup is that 1 hole in it. And I'm talking about the surface, just the outside of a coffee cup is the same as the outside of a donut.
So can you eat the coffee cup? If it's made out of donut, then you can.
I'm talking about mathematically equivalent to, I'm not talking about food. So there's lots to it here, but in terms of simple terms, if the planar graph you can work Euler characteristic and it will be 2, but you can do Euler characteristic for other sorts of things too, and that's one way of working if something's planar or not planar. So So as I said, for a planar graph, the order characteristic, which is that sort of thing there, is equal to 2. And people have done lots of stuff here. So non-planar graphs either contain that sort of graph inside of it, or they contain the complete graph of 5 vertices. They're the two simplest problem cases, essentially. Anything else would contain either of those. So that's the computer's way of trying to draw what I did before.
So basically, what's going on here?
It's just a whole bunch of donuts, really.
G with the G.
So you can do other sorts of problems, as I said before. That one thing you can do different things in a graph. You can try colouring them. As I said, that's useful in like colouring graphs. Seems like a kiddies exercise. As I said, that actually corresponds to doing things like producing a timetable, which is corresponding to colouring a graph. But other sort of problem is if you've got a planar graph, something you can actually draw on a piece of paper. So any map of an atlas, for example, corresponds to a planar graph. So each country, if you have a map of a bunch of countries, each country would correspond to a vertex. If two countries share a border, they would have an edge between them. And so if you're able to draw it as a map, it has to be a planar graph. So a theorem that exists that you can colour one of those in. So what is colouring in? Colouring in means you can basically colour each vertex in a different colour. So if two adjacent vertices must be a different colour, the theorem states you can colour it with at most 4 colours. You can do sometimes less, but you only need 4. Just the 4 would do it. Now if you call that a real atlas, they tend to use more than 4. For very reason, because they just like more colours probably. But you can actually just do it with 4 colours.
Really?
Now, so we pick our planar graph, our handbag over here.
It's a Pac-Man.
So let's try colouring it. This vertex will pick one colour, green. It's adjacent. Anything which is adjacent to it has to be a different colour. So this one has to be different. That's blue.
Red.
That one can be different. It has to be different colour. So it's blue, and this one over here can be red. So you actually can colour this one with just 3 colours. So every adjacent. Doesn't seem right, and I got no reason why. Just drawing the wrong ones up. So that's green.
Black hole there.
So when I actually draw the complete photograph properly and multiple edge, it really does force to all vertices have to have be a different colour.
I was wondering why there was only 3 colours.
So you can't, because I draw the edges properly, there's no way of having less colours. So every 2 adjacent vertices, so one connected by an edge, have to be different colours. So you see, I really do need 4 colours in this case for it to work. And so some people prove that. So what's worth explaining is how they proved it. People that had a guess that this might be the case a while back. They certainly could prove it simply that 5 colours would certainly work. They go, I think you only need 4, but it's hard, I can't really see how to prove it just yet. So they guessed it. That's called a conjecture. Conjecture makes it sound fancy, but pretty much it's all it means. I'm guessing. I think it's true, and we'll see if someone else can prove it after me because I can't work out how to do it. And so some of the guys came up in the 70s, and they thought of a bunch of ways. They go, well, we'll try to prove it. And they did it by grunt work, essentially. They came up with a bunch of minimal counterexamples. So if there's going to be a counterexample to it, it's going to be one of these, about 2,000 cases. So it was that sort of order.
Our colour man.
And that's it. But they go, well, it's a bit hard. That's a lot of cases to consider all those different options, all different colours for those almost 2,000 cases. So what they did is they got a computer to do it for them. So they essentially got a computer to check each of those cases, and the computer would check all the coding options for each case.
The computer lied to me.
And so that's what they did. They basically used a computer to prove the result for them, effectively. And they published it, and people said, I'm not quite sure to believe you, because it's pretty hard for... You haven't actually done it. You haven't checked it yourself. You've only got a computer to check it. How do I know if the computer's done the right thing? So it wasn't very well accepted initially.
Well, it's like anti-vax.
Now that people have programmed
People are anti.
mathematical proving software, etc., people are more accepting of the result, and it's still upheld, so people still think it's so valid. But so the more interesting thing here is that people have used computers to assist with mathematics. With it all. But there's lots of different things with aspects with graphs. So how do you represent them? So a useful thing is called an adjacency matrix. So I'll do some examples and I'll fill in the details.
It's wrong. Who the hell did that?
So here's a graph. Let's just give some labels: A, B, C, D, E. So a matrix. What do you think a matrix is?
Something.
Anything more details than that?
It's a movie with 2 sequels.
Which were terrible.
Yeah, animated.
Okay.
Don't even acknowledge that. No.
Matrix
16.
has the same. Bizarrely, has the same STEM word as a matriarch. It means giving birth. That's actually where the word comes from, which is completely unhelpful to work out where it is. It just means a rectangle of numbers, essentially. So a rectangle of numbers, that's what we will take it to be. So I'm going to have my rectangle of numbers over here in a second. Maybe just make it bigger. They're very useful things. So if you do Maths 101, which some of you guys will do, they're certainly useful. And they get mentioned in Maths 101. Things like GPUs, that's what they deal with. So GPUs would deal with matrices all the time. So they deal with rectangles and numbers, and that's how they show the graphics on your computer, among other things. So what I want to do here is I want to do an adjacency matrix. So the adjacency matrix pretty much has, for every vertex in our graph, we have a row. So I'll just label them. So A, B, C, D, and E. So I've got 5 rows here. Each row will correspond to one of the vertices. And I have a column as well. Each column corresponding to each of the vertices. So the adjacency matrix actually is square, but matrix in general can be rectangle. But so I've got a square matrix. And then for every, I'll have 25 numbers here in the end. So it's going to be a grid of 25 numbers. Each of these numbers, so just picking one over here, that would be the number of edges which connect from the row to the column. So this first one here will be the number of ways of connecting A to A.
That'd be a solid 0.
There's none, so there's no edges there. This one over here would be the number of ways connecting A to B.
That'd be a solid 0 as well.
Yep. A to C.
1.
1, so we've got something for a change. A to D.
0.
And A to E. 0. See if you can do the rest of it on your own piece of paper.
E's and just make them all 0 because no.
Do your own piece of paper. See if you can fill the rest of it in. So work out what the rest of these.
Well, I think anything with an E in it is just going to be a solid 0. So
Okay.
Good work.
Let's be honest there, come on.
Okay, so that's all the E's done.
They're little loopy things, so you can chuck wherever it's like the
Yeah,
B to B, just chuck zeros or C to C.
So there's no loops. So it's good to see the patterns here. So there's no loops. There's a 0 down the diagonal, as it's called. So the diagonal, we only consider one diagonal. The diagonal is the top left to the bottom right. So we don't have, that's only one diagonal in a matrix, which seems odd, perhaps, but so for a simple graph like this one, So symbol graph means there are no little loops on vertices. That means you get zeros down the diagonal, as you can see here. That's one pattern you can see. So if something is completely disconnected, so you get those rows of zeros. What are some of the other numbers? Let's do this one over here. What's B to A?
0.
And C to A?
1.
And D to A?
0.
0.
Oh, I see it.
So another pattern you might notice is if you go along a row or down a column, you get the same numbers. And that happens for undirected graphs, so directed graphs that may not be applied for. But if you get, so if it's the same going across or down a column, it's called a symmetric matrix. So undirected graphs are symmetric, directed ones may not be. That's another pattern you can see. So if you go along a row, you can just automatically copy the numbers going down as well. So what's B to C? 1. So putting a 1 here automatically forces a 1 over there at the same time, using that symmetry. And B to D is 1, forces a 1 down there.
0.
C to D would be 0, and that forces a 0 down the bottom here as well.
Oh, look at that beautiful. The matrix.
Wow. So that's a matrix. So that's called the adjacency matrix. So the adjacency matrix is a square of numbers, and each row and column corresponds to one of the vertices. You list order them the same way, of course. And the number there would be the number of edges going from the row to the corresponding column. And these things are, you can do some calculations with them, which we'll do in a second. Here's a new graph, so same data points, just a few more edges onto it here. How does this change what the adjacency matrix looks like?
E won't be all zeros.
So E won't be all zeros anymore, that's right.
Probably more ones.
Probably. You never know.
So tell me some of the entries that get changed.
Well, A to E is 0. Oh, it still goes to 1.
So A to E will be 1,
Or E to A goes to 1.
and by symmetry you get the same bottom square at the same time.
Yep. C to E goes to 1, and E to C goes to 1 as well.
And as you can see, so that's an extra edge that we had before, so we'll put that on. Other extra edge is this one, C and E.
Yeah.
So that'll be 1, that'll be a 1.
Yep.
Anything else being added?
I don't think so.
That's it. So some other patterns to notice is for simple graphs like these, you only get zeros and ones. That's all you get. So in order to get numbers higher than 1, it needs to be a multiple graph where you're usually allowed to have multiple edges. So this is a multiple. This is a multiple graph. So a multiple graph because it's got some more edges. So in addition to what we had before, we've got the bottom here and another one down the bottom. Just looking how it changes things. So we've got a D to E added now, which would be you'd have a 1 here and here, on this edge. And this one over here, the one from E to C, how does that change things?
B to C. There's 2 C.
There's 2 rather than just the 1.
Yeah, so now from E to C, now we have 2 entries, 2 edges, rather than just the 1 or 0 as it was before.
The 2.
And so at the multiple graph, you can see you can get other numbers higher than 1 cropping up. So that's called an adjacency matrix. So some other patterns, you can do the same thing for directed graphs in a similar fashion. So it's from the row to the column, and you can get things not symmetric anymore. How do you get zero? How do you get things not zero on the diagonal? Loops. So that's the diagonal there. And the only way of getting zeros off that is to have a loop. Any loop would create a 2 there.
Unless it was direction.
Yeah, so it's the number of, there'd be 2 things leaving, 2 things coming in. And so, let's do a few things. So, say you did the total of a row. So you added up the first row there, for example. You get 1 plus 1.
2.
Gives you 2. That corresponds to the degree of that vertex. Or more, if it's directed, it would be the out degree of that vertex in general. And you could do a total of other things. So you could do a total of this column. So 1 plus 2 plus 1 gives you 4, for example. So the degree of E down this new graph over here is 4. So this adjacency matrix, by adding numbers either along the row or down the column, gives you corresponding degrees as well. And as I said, those degrees are useful to work out if you can be traversable, for example, among other things. So some uses for adjacency matrices. You can also use adjacency matrices to count the number of paths. So sometimes you might go, well, how many paths are there which are of length 2 in a whole network? Well, how many paths are there from D to C of length 2? Now you probably can count them. There'll be 3 of them, I think, in this case. But it'd be nice to get a nice systematic way of doing that, and we can use the adjacency matrix to help us out. So before I want to do that, I want to explain a bit more mathematics. So I want to talk a bit about matrices in general. Just before I do that, I've got this example, so let's do that one. Given an adjacency matrix, you can also go back to write down a corresponding matrix from it. So let's just do this last example, which I've forgotten about. So this is an adjacency matrix. From this we can write down a matrix. So it's good to just label them. So we think of it as A, B, C, D, etc. You can call it anything you want to. What do we call that? Let's just do A, B, C, D. Just go around clockwise. So you've got to label some vertices. If I label them differently, I would get an isomorphic graph. It'd be equivalent. It might look a little different, but it's isomorphic in the same thing. It's for each other. So now we've got to try to go from our adjacency matrix to just drawing some edges on this graph, essentially. So, what does this 0 here tell you?
There's no loop on it.
No loops, so I don't have to draw them. What does that 1 there tell you?
Goes one length.
So there's one edge from A to B. And by symmetry, we've done that one as well. So there's a 0 here, means you can almost ignore it. Draw. What does this 2 correspond to?
There's 2 to A.
There's 2 edges, A to D. Yep. Two lines, edges, same thing. So those ones are done by symmetry. What does that 2 there tell you? So you got a loop, so it's leaving and coming in, so that's why you counted it twice. So you've got one loop, which has 2 ends coming from B. So which is another way of saying there are 2 ways from going from B to B. Either you go forwards along that edge or backwards along the edge. That's why the 2 there. Think about it. What does that 1 correspond to?
1 minus C.
Yep. So 1 edge from that. Zeros we can ignore, and the only thing last is this one over here, really.
D loop.
So you've got a path from C to D. And you can do things like and then you can use the matrix or the graph, whatever you want to work out if it's traversable or not. To work out the degrees, for example, we can just add up if you add up those entries, 1 plus 2 is 3. 1 plus 2 plus 1 plus 0, 4.
2, 3.
So if you look at there the degrees, you can see 2 of them are even, 2 are odd. So and those 2 odd ones, that suggests that is traversable. So you can traverse it from starting from A and ending at D or the other way around. So it is certainly traversable. Go back to what we did before. So the adjacency matrix, so a graph and an adjacency matrix here really are equivalent to each other. So you can just there's just a neat correspondence between the two of them. Now, adjacency matrices might have lots of zeros in them. So it has lots and lots of zeros, it's called rather sparse. And so sometimes, so you could internally represent a graph by a matrix. Right? That's one way of representing inside a computer, the data structure you might use. But if you don't have that many edges, there's so many zeros, it's just a bit of a waste of space. So computer scientists have thought of other ways of representing graphs in computers, which we may not talk about, probably run out of time to talk about today. But so thinking about how to represent these things does depend on how many edges you expect to have. But I want to have a little digression about matrices. So I said a matrix really is a rectangle of numbers. We're going to focus just on the square ones in this subject, but you can do rectangles in general. The number of rows and columns are different for other sorts of purposes. Matrices are useful in maths for other reasons. They crop up here. They are more useful generally. Like other mathematical objects, you can combine them in different ways. So you can add them, you can multiply them, you can divide them sort of, and you can certainly subtract them. So you can do various things with them. I won't try to explain the dividing bit. That's just another, you can do that in another subject. The two I really want to mention is adding and multiplying, because they're the sort of two things that apply in what we will look at. So consider two matrices. So I'll make it in the context of what you're doing in terms of networks. So imagine we've got 3 locations. So Orange, Bathurst, Wagga, for example. So Orange, Bathurst, where I live and work, and Warwick is campus, just think big on, to make it a bit more interesting example. Suppose the first one really is the adjacency matrix, and it would be a directed graph in this case, so it corresponds to a directed graph, of the number of buses that travel from one location to another. So reading along the top row here, from Orange, there are no buses which leave Orange and go back to Orange. There's no loops in the system. There are 2 buses that go from Orange down to Bathurst, 5 buses which go from Orange down to Wagga. So that's what the first row corresponds to. So each row is the from, each column is the to. So the first column here is to Orange, there are no buses from Orange. From Bathurst to Orange, there'd be 1 bus. From Wagga to Orange, there'd be 6. That's what it corresponds to. So it's a directed graph in that sense. And that's the first one. The second matrix is the same, but for flying instead of catching buses. Can we work out a matrix which shows the number of ways of going from one location to another, either by a bus or a plane? So one or the other. The answer is yes, you can do it. How do you do it? Just
Add the column, added together, each grid together.
So all you have to do is it just really corresponds to adding the matrices together. So the number of ways of doing one or the other really is actually worked out is adding them. And so the way to add matrices is fortunately pretty straightforward. So adding matrices really just means adding each component together. So it's called adding component-wise. So adding 2 matrices will give you another matrix normally. Or will always give you another matrix, I should say. So this matrix would have 9 entries in it, so you have to work out all 9 numbers. So this number at the top here would correspond to adding the corresponding numbers in the first 2 matrices. So it would be 0 plus 0, which is 0. Next number along
3.
will be 2 plus 1 is 3. 6. You rattle them off probably.
2, 0, 2, 8, 1, 0.
Okay. So that's really adding component-wise. So adding one component at a time. And so adding two matrices is fairly straightforward, which is nice. So it's good to have some simple things. Next thing you want to do is to multiply matrices. This is a harder problem because it's not multiplying terms at one term at a time. Okay. So let's consider the same two matrices again. Different problem then. How many ways are there of catching a bus and then catching a plane? So let's say we want to start in orange. We want to catch a bus somewhere. We don't really care where we're going. And then it has to be either orange, Bathurst, or Wagga. Then from that new location, we then have to catch a plane, finishing up at Wagga. How many different ways are there of doing that? How many ways of starting in orange, bus somewhere, plane somewhere, and then finish in Wagga?
Do you have to plan, or can you just...
Yeah.
You have to get it. So go fast. And it's going to go from orange to Bathurst to Wagga.
So let's just think about some ways of combining it. So this is a simple problem, and we'll try the more general one in a second. So this first row here is the number of ways of catching a bus from orange. So you have to be one of those situations there. And then this last column here is all the number of ways of catching a plane to Wagga. That makes sense? The first one was bus, the second one was planes. Rows correspond from, columns correspond to 2. So they're the two things I'm interested in really for the moment. So you want to catch a bus from orange, somewhere else, plane into Wagga. So let's think of all the different choices we want. So I'm going to write them down separately. I wrote them sort of stylistically here. How many ways are there? Well, one choice is if you're going from Wagga, you're only going one intermediary spot. So you're either going to go via orange again or Bathurst or Wagga. They're the three choices really. So if you're in if you're going from orange to orange, there'd be 0 ways of catching that bus. And then, just to be pedantic, let's just catch a plane anyhow. How many ways are there catching a plane from orange to Wagga? 1. So you want to make both those choices. So it'll be 0 times by 1, which I'm sure you can work out. There's no way of doing that. Alternatively, the other option would be to go via Bathurst. So if you're going via Bathurst, there are 2 ways of catching the bus from orange to Bathurst. And once you're in Bathurst, how many ways there are flying? So it'd be 2 times by 1. Or you could go via Wagga. So there'd be 5 ways of catching a bus from orange down to Wagga, and then no ways of flying.
Wagga from Wagga.
Through Wagga from Wagga, that's right.
I hope so. We made it to Wagga. Fly to Wagga.
Just get in the plane.
So if you add up those numbers,
Oh, we have arrived at our destination.
so you got 0 plus 2 plus 5 gives you 2. So rather simply, there are only 2 ways of doing it. But I wanted to suggest the more general pattern here, and that is the way to sort of combine these networks together. Really is going along a row and down a column. So along a row, down a column. That's what we're doing, along a row, down a column. What I'm doing is I'm multiplying matching numbers up. So I've done the 0 and the 1, 2 and the 1, 5 and the 0. So it's multiplying matching numbers up and add them all up. That's sort of how I've combined them together. If they were longer rows or longer columns, you just have to combine more things together, essentially. And that sort of process really is about how to combine 2 networks together. And so if I want to do it, more comprehensively. So let's just do it more generally.
Does it matter what row or column you use?
I'll do all of them at the same time.
Yeah, because you choose a row and then choose any column you want.
So what I'm going to do is, that was just a little prototype example. I want to do the more broader thing. I wanted to multiply the two matrices together. So this is called matrix multiplication. And it's not like addition, it's much harder than addition. You're just going to add the numbers up. You have to do something like what I was explaining there. So how I would do matrix multiplication in practice, like on a piece of paper, is draw it like I've got down the bottom of the screen here. So I'd do the first matrix sort of down the bottom, leave a big amount of space here, and then put the other matrix at the top. Order makes a difference. So if you chop the order around, you get different answers. So order makes a big difference, so make sure you get the order right. What's going to happen is when I multiply these two matrices together, I'll get a new matrix. So essentially they're both adjacency matrices, I'll get a new adjacency matrix. So it's another rectangle of numbers at the bottom there. And so this space I've left here will be the answers. That's where the answers will be. And so what we worked out this number over here. So we went along the orange row down the Wagga column, and we worked out the number here was 2. That's the number we worked out a second ago. So that same sort of process I want to do for all the other 8 numbers I want to consider here. So let's just do some more. So let's just do this one here, for example. So this is the number of ways of catching a bus from Orange to somewhere else, and then catching a plane back to Orange. That's what it corresponds to. So I'll do the calculation on the side here, but there are no ways of catching a bus from Orange to Orange, and then there are no ways of catching the flight back to Orange. So 0, so going along the row down the column, so 0 times 0, just matching up the two numbers, multiply them up. The next number is 2 and 1. So there are 2 ways of catching a bus from Orange to Bathurst, and then there's 1 way of flying back to Orange. And keeping along, the next numbers are 5 and 2. So there are 5 ways of catching a bus to Wagga, and then 2 ways of flying back. So there are all the number of different ways of catching a bus from Orange to somewhere else and planing back to Orange. So if I add up all those, if I add up that expression, what do I get?
12.
12. That would be the number in this particular case. And I could do the same thing for all numbers. So how about I do one more and then I'll let you do the rest. This one over here, this one's easy for me. You'll see why in a second. It's got to go along the row, down the column. Always along the row, down the column. So it's the numbers, so 0 and 1, multiply them together, add the next one.
Just a whole bunch of zeros.
Yep, so it's going to be 2 and 0, multiply them together, add the next one, 5 and 0, add them up, you get 0. So that one's nice because you get a bunch of zeros pretty quickly. They're not always that nice. So how about you have a go, spend a few minutes to see if you can get the rest of this new adjacency matrix, essentially. So the tips are, go along a row, down a column, and the corresponding row and column you're going down to is where you're going to work out the number, essentially. Multiply the matching numbers up, and then add up all these different types to do. That gives the resulting number.